Hello guys, so welcome back to our VHDL lessons. Now it's time for a bigger design for the comparator, which is basically the 4-bit binary comparator. Okay, so in that design, as we explored in the lecture, we have still 2 inputs and 3 outputs. The outputs is just 3 bits, and the inputs now, which is still 2, but each one is 4 bits. That's why it's called the 4-bit binary comparator. Okay, so we ended up that we're gonna use, as we explained in the lecture, we're gonna use 4 1-bit comparators of structural design. Each one will compare each corresponding bits in A and B. So for example, this guy here will compare A0 with B0, and it will give us 3 indications. A0 means A0 if it's 1, this means A0 is equal to B0. If L0 is 1, which means less, that means A is less than B, or A0 is less than B0. And G0 means that A0 is greater than B0. For example, when A is 1 and A0 is 1 and B0 is 0. Okay? Then we're gonna use all these signals, 12 signals, 12 indications, to build a bigger decision, about A and B in general, as a 4 bits and the 4 bits. Okay? So this circuit called final decision circuit, okay, will use all these signals to build, the 3 bigger decisions. Either A as a whole, I mean the 4 bits, is less than B or greater than B or is equal to B. So basically, in this code here, this basically this circuit that we're gonna implement here in this VHDL code, this is the first, comparator. This is the second comparator, third comparator, fourth comparator, and this part here, let's draw it with, or let's highlight it. This part here, this highlighted part, is basically what's inside the final decision circuit. Okay? And if we wanted to drive equations for these, okay, the equation would be something like this. Okay, 3 equations, one for the less, the first one here, one for the greater, the second one, and one for equal, which is the third one here. Okay, and that's basically what I have done here in this VHDL code. So in this VHDL code, we have first the entity, in which we define the inputs and the outputs of the total design. So if we look here, this is the 2 inputs, and this is the 3 outputs. Our 2 inputs are, each one is 4 bits, so that's why I'm defining them as standard logic vector, 4 bits. And the 3 outputs, each one is just 1 bit, so all of them are out standard logic. Okay. Then I define here these signals. This E0, L0, G0, So I define the 3 signals. One is called E, one is called L, one is called G, and each one is 4 bits. Okay, so E of 0 is basically E0 here. E of 1 is basically E1, this signal here. E of 2 is E2, E of 3 is E3, and so on for L and G. L of 0 is L0, L of 1 is L1, and so on. Okay, good. So let's now define, we need here 4 binary comparators. So let's define them. So I make a package out of my 1-bit comparators that I showed you last lecture or last lesson. Okay, and I include it here in our digital component library. And here is, the 4 instantiations. So here is the first instantiation. We need a comparator in which we're gonna enter as inputs A of 0 and B of 0. And the outputs will be E of 0, L of 0, and G of 0. And the order is very important. Okay, if you recall our previous design in our last lesson, the first output was E, the second output was L, less than, the third output was greater than. That's what, if you switch, it will be horrible. You will get wrong output. Okay. Then the outputs of these, comparators, these guys here, the outputs of these will go to the final decision circuit. The final decision circuit is just 4 equations, okay? Or what's inside here is just 4 equations, which is basically that thing here, or these, these, AND gates and OR gates and stuff. This is basically the 4 equations, okay? So basically, I'm writing them here as well. So here is the 4 equations. If we go back to our lecture, in our course, the lecture part, and you will find how I could, derive these 3 equations. So L is equal to L3 or E3 or E of 3 and L of 2, or E of 3 and E of 2 and L of 1, or E of 3 and E of 2 and E of 1 and L of 0. So that's basically what I have done here. L of 3 or E3 and L2, the second term, then the third term, and finally the final term. G is just L, exactly the same, G and L here. Okay, just remove L and put G. So come here and paste it, and I remove the L and put G. That's what I have done. Very simple. Finally, the E, equal, this is basically ANDing the 4 E signals together. What are the 4 E signals? This is basically E0, E1, E2, E3. Or here, E of 3 and E of 2 and E of 1 and E of 0. Very simple. Okay? Now for the test bench is also simple. So here is, I have the, the same entity of the design. So just copy and paste that into here. Okay? Then I define 5 signals because I have basically 2 inputs and 3 outputs. Here I'm instantiating the designs that I want to test and pass to it the signals that I'm going to use to give inputs and read the outputs. Okay. And here I'm looping over all the possible combinations of the input. So the input, remember, we have 4 bits. So we have 256 combinations. Okay. So I loop for A from 0 to 15, which is 16 combination. And for each loop of A, or for each iteration of A, for example, when A of 0, B will span 0 to 15, another 16 combinations. That's why we have 16 times 16, we have 256 combinations. Okay, so if we run the simulation, here it is. So let's take it case by case. For example, when A is 0, as you see, guys, here, let's, when A of 0, look, for all possible values of A, for all, in that case, when A is 0, look, B takes all possible values from 0 up away to 15. When in the first cycle, A is 0 and B is 0, then the equal signal will be 1, which is the yellow signal here. And the other 2 signals will be 0. Then, when A is 0 and B become 1 now, it's less. So the equal signal will go back to 0. And now the less signal will be 1. And the greater signal will be 0. Then the rest will be the same as well, because 0 is basically less than everything from 1 up to 15. Let's now check the 1. The first bit, 1 and 0. A is 1, B is 0. So basically, the equal signal is 0. The less signal is also 0 because A is greater than B. And the only signal that is 1 here in that cycle is the greater signal, A greater than B. That's why it's 1. Then, second cycle here, A1 and B is 1. So they are equal. So the equal signal, the yellow one, become 1. The less signal becomes 0. Still 0. It's continue 0. And the greater signal becomes 1 and 0 now. So it goes down from 1 to 0. Then from here to the rest of the combinations of B, the values of B, A will be less than B because 1 is less than 2, 1 is less than 3, 4, 5, up to 15. Another case, when A is equal to 2, 2 and 0, A is greater. That's why the violet signal, the third signal is 1. 2 is greater than 1. Again, the violet signal is 1 and the rest is 0. Then 2 and 2, the equal signal become 1. The less signal is 0 and the greater signal becomes 0. Then from that cycle to the 15 here, A will be all the time less than B because 2 is less than 3, 2 is less than 4, less than 5, less than 6 until 15. So in all from here to here, the less signal is 1, the other signals are 0. We can continue with that until we reach, 15. Here is the last, set of combinations. So here is A is 15 and B will take from 0 up to 15. Okay, so from when B is 0 up to 14, A is greater than B. So we're gonna see, look, 15 and 0, A is greater than B is 1. 15 and 1 until 15 and 14. In all such cases, the equal signal is 0, the less signal is 0, and the greater signal is 1. Then finally here, the final combination, A is 15, B is 15, then the equal signal become 1, the less signal still 0, and finally the greater signal becomes 0 again. Okay, guys, that was basically the 4-bit comparator. It's really interesting design. Thank you very much for watching this video and see you next week. Bye-bye.